Welcome back to my channel. My name is Chaki and today's lesson is going to be on bending moment. Now what is bending moment? Like the shear force, it is also an internal force which is generated in a beam or a structure to resist some kind of external force. So what is bending moment? Bending moment at any cross section. Now when I'm calculating a bending moment, we always need to consider the cross sectional region. So every point, or should I say every cross section, bending moment will be different. That is, bending moment will change according to the type of loading as well as throughout the length of the beam. Bending moment might change or may remain same. So what is bending moment? Bending moment at any cross section is a resultant moments of all the transverse component of forces. Here transverse component of forces means all the forces which are acting in the body. Say for example, I am considering this particular beam. Therefore loading in this particular beam will be in such a manner that the load acting on the beam, say this is the load P, the load acting on the beam will be transverse, that is perpendicular to the longitudinal axis of the beam. So resultant moment of all the transverse component of forces about that section, either from left or from right of the section. Assumptions involved in theory of simple bending. First is the material is homogeneous, isotropic and linearly elastic. What does homogeneous mean? Homogeneous means density and other properties at all point is same. What does this mean? Say for example, I am taking the same beam. This beam is made up of multiple particles, of which I am considering only 3 here. Particle 1 is at the bottom region, particle 2 is at the top region and particle 3 is somewhere between them. In this beam, I can see that particle 1, particle 2 and particle 3 will be same in terms of density and any other property of the material. If it is same in terms of density and any other property, then I will say that the entire beam or the entire body is a homogeneous one. Also, what is the meaning of isotropic? Density and other property in all direction is same. What does isotropic means? Say for example, I am considering particle 1. Now particle 1, the property of particle 1 will be same in direction x. It will be same in direction y. Also it will be same along the direction z. Similarly, for particle 2, it will be same. It will be same along x direction. It will be same along y direction. Also it will be same along z direction. So here I can see that particle 1, its property, that is density and any other property, will be same along the x direction, y direction as well as z direction. Now for particle 2, same thing will happen along x, y and z. Along all the direction particle 2 will be same as for particle 3. So properties of each of the particle will be same in all direction, that is x axis, y axis and z axis of this individual particle will be same. Therefore by considering these two, I am making sure that the beam is particularly made of a single material and there is no variation in those material. Also I have considered that it is linearly elastic. What does this mean? It means linear elastic means that the stress and strain variation will be linear, that is it will be a straight line. Here A is the proportionate limit in this graph. If we plot stress versus strain, I will see that point A is a proportionate limit, point B is the elastic limit and AO is a straight line. and its slope is called Young modulus. So what does this mean? It means when I am applying a load in the same beam, this is the beam, okay. Now what is the kind of load? It might be tension, that is I might be pulling this one, or it might be compression. Here this is the compressive force. Now what does linear elasticity mean? It means whether it is compression or it is tension, the body will regain its original shape on removal of this tension or compressive load. So point V will represent the maximum stress up to which a specimen regain its original length on removal of the applied load, which is tension, this is tension or compression. The body will regain its original shape. And AO is called the linear elastic region. AB is a non-linear elastic region, but its variation is so small that we consider it to be straight. But it is a non-linear elastic region, where AO is the linear elastic region, and the slope of this AO, that is slope of this straight line AO, linear elastic region, is called Young's modulus. It is a very important point. Point 2, plane section, that is the cross-sectional area. If I consider this particular beam, the same beam, I am considering the same beam here, this is the beam. So its cross section is this is the cross section of the beam, okay. Now this assumption is what? Point 2 assumption is what? Plane section or cross sectional area before bending remains plane after bending. What I am trying to say is that, for example, if this was the beam, I am bending here, I am bending either this way or this way. This is bending, this is also bending, okay. Now what I am saying is that before bending and after bending, the cross sectional area will remain the same. So if I take the example of same beam, say this was the same beam as I have considered. After bending, this is what happens when I bend the beam. When I am bending the beam, when I am bending the beam like this, the upper region is getting compressed and the bottom region is in tension. Here you can see it is compression in the upper region, and in the lower region it is tension. How it is happening? When I am applying moment like this. When moment is applied like this, it is compression in the upper region and tension in the bottom region. So what is happening here? We are actually bending the beam. So I am saying this cross section after bending, if this is the cross section after bending and this is the cross section before bending, both will remain the same. Why we are doing so? Let us see that. Now this is a 2D figure. This is the beam. We are applying the same moment here. So after bending, the deflected shape of the beam will be looking like this. It will bend in a U shape. Now suppose we are going to superimpose the original shape of the beam with the deflected shape of the beam. It will look like this. Here we have superimposed both this original shape of the beam and the deflected shape of the beam. So we will get a figure like this. From this figure, I have assumed that cross section, that this particular region is actually the cross section. Both are the cross section. This one and this one also is the cross section. So before bending, the cross section was straight. After bending, it has inclined at an angle, but it still remains the same. Why we are doing this? To get the linear variation. Now if we consider this side, say this particular side, I can see that the strain variation is linear. For example, if this was 2x, that is from this point, which is the neutral axis, I'm coming after that, what is neutral axis, say from this point to this point, it is 2x, and here the strain is 2 epsilon. So at a distance x from the top, or from at a distance x from the bottom, it will be only epsilon, because the strain is varying linearly. So what is neutral axis? Neutral axis is the line at which neutral surface cuts the cross sectional area. Now if I consider the same beam, if this was my beam, this is the neutral surface. How can I say a particular surface is a neutral surface within the beam? We are going to apply the same principle. Now I'm going to take the same beam and I'm going to apply the moment. After applying the moment, I will see that the beam has bended. How it has bended? It has bended in a way that the uppermost region will be in compression, and due to this compression, the uppermost layer of the beam has decreased. That is, the length of the uppermost region has decreased. Also, for the bottommost region, the length of the beam has somewhat increased. Now if we see the same thing in 2D, it will be more clear to us that here, due to compression, the uppermost region has decreased. At first it was this, you can see here we have superimposed this. At first it was straight, now due to compression it has decreased. At the bottommost region it is tension. At the bottom I can see that the length of the beam has somewhat increased. Now between this decreasing length and increasing length, there will come a fiber in this beam, or a plane in this beam, where it has neither increased in length or has decreased in length. That particular surface or that particular plane is called the neutral surface. Now the neutral surface for both the deflected and undeflected, that is the original beam, will remain same. Here I can see this straight line is the neutral axis of the original beam. This curved dotted line is the neutral axis of the deflected beam. Now the shape of the neutral axis might have changed, but the length will remain the same. So it is the neutral surface. Therefore, in this beam, I am representing the cross section here and the neutral surface is here. So if I intersect these two, the plane where the neutral surface and the cross section is meeting, that is in between this region, is called the neutral axis. So if this is the cross section, like I have shown in this case, and this is the neutral surface, its intersection will give us the neutral axis region. This is the neutral axis. So this NN is also the neutral axis. When I am considering the beam in 3D, I will say that this particular hatch region is the neutral surface. When I am considering the beam in 2D, I will be seeing the beam like this. I will be seeing the beam like this. So this is also the neutral surface or the neutral axis. As I have written here, neutral axis, it is a line at which the neutral surface cuts the cross-sectional area. At the neutral axis, there is no tension and there is no compression. Why? Because there is neither increase in length nor decrease in length. So there will be no tension and no compression. And at the neutral surface, there is no change in length of the beam. Now for point 3. Cross-sectional area is symmetrical in the plane of loading about an axis through which load passes. That is, it means that the load passes through the centroid of the cross-section. If I take this T section, this is a T beam. So if I take this cross-section and try to divide it through its centroid, I will see that this particular T section is symmetrical. That is, it can be divided into equal half. So when the load is passing, it is passing through the centroid of this cross section. This is the load here. This is P, this is also P, this might be F, this might be say this might be a K. These are all load. All of the loading are passing through the centroid. Now for point 4, Young's modulus in tension is equal to Young's modulus in compression. As I have discussed previously, in the stress strain region, if I apply load, the nature of the loading might be tension or compression, but right after removing of the applied load, that's when I am removing the applied load, whether it is compression or tension, the specimen will regain its original length. So I'm considering that Young's modulus, that is slope of this line AO, will be same in tension as well as in compression. Now for the sign convention for bending moment. So when I am applying moment like this, it will be sagging. Let me demonstrate you. Consider this particular ruler to be a beam. So when I am applying moment like this shape of the beam due to bending moment is called sagging. Here you can see the sagging bending moment sign. It is like a U shape. This particular top will be concave and the bottom will be convex. It is positive. Similarly, if we are applying the moments in opposite direction of previously what we have applied, like this, the shape of the beam will change in this manner. It is hogging bending moment. In the hogging bending moment, the upper region will be convex and the lower region will be concave. It is negative. So we represent hogging bending moment as negative. Now, this is a tip. So we all have a smartphone right now, right? In these days, we all have a smartphone and we use a certain emojis, right? This is happy face, suppose. And this is sad. Why I am saying it is happy face? A happy face will indicate sagging bending moment, whereas a sad face will indicate a hogging bending moment. So a sagging will be positive and hogging will be negative. This is a tip for how you can remember sagging and hogging. We actually represent it like this: concave and convex, positive and negative. Thank you. That's it for today.